Okay, thank you very much for the invitation and opportunity to speak here. So today I will talk about cluster algebras and tilings for the m=4 amplituhedron. Okay, so today we'll talk about these two objects here. You might have seen these objects here, but this is only a specific type of what I'm going to consider. This one may be new for you. So on the left-hand side, we have an object called the amplituhedron that was introduced by physicists in 2013. And this was an object that geometrizes scattering amplitudes, which are probability of interaction of particles in a certain quantum field theory. And the amplitudes are kind of like related to, are computed as volumes of these objects. On the other side, we have cluster algebras introduced by Fomin and Zawilski in 2002. And they are a class of commutative rings with a set of distinguished generators called cluster variables and have remarkable combinatorics. They were introduced to study total positivity, Lie theory, etc. And also lots of cluster varieties that we like, cluster algebraic varieties that we like have a cluster structures like Grassmannians, flag varieties, and Schubert varieties. But also, these cluster algebras were also appeared in physics to describe singularity scattering amplitudes. So today I will show that these two things, these two objects are connected. And in particular, the amplituhedron is also interesting from a mathematical perspective because it is a semi-algebraic set which generalizes polytopes inside the real Grassmannian and also builds on the theory of total positivity and matrix theory. And also, it's part of the recent general framework called positive geometries. Okay, so these are the two main papers that I'm going to consider. And the work is joined with my collaborators, Evan, Zohar, Lacrec, Sherman Bennett, Tesler, and Williams. And you will see this long acronym all over the talk. Okay, I will start with defining what the amplituhedron is, which is the first character of the story. Tell how we want to tile the amplituhedron and understand tilings. Then I will introduce cluster algebra for the Grassmannian and understand how the amplituhedron and cluster algebras are connected with each other. Okay, so let me introduce the Grassmannian, which is the object, and the positive Grassmannian, which is the object in the background. So let me fix the notation. The Grassmannian k, n is a space of k-planes in n dimensions, and we can represent an element in the Grassmannian using a full rank k times n matrix up to row operations. And we can use certain coordinates called Plucker coordinates, which I will denote as angle brackets I, which is the k times k maximal minors of the matrix C, where I is just the column set I use to compute the minor. As an example, this is a matrix 2 times 4 full rank that is represent the points in the Grassmannian 2, 4. And the angle brackets 1, 2 is the minor computed with the column 1 and 2, so which is 0. And this is minors computed with column 1 and 3, which is 1, and so on. So we get a whole list of things. Okay, today I want to focus on a nice subset of the real Grassmannian, which also we've seen in previous talks this week, called the positive Grassmannian. Informally called the positive Grassmannian, region is called the totally non-negative Grassmannian. And I'll denote it as gr k, n greater or equal than 0. And it's a subset of the real Grassmannian where all the Plucker coordinates are non-negative. And we want to partition this positive Grassmannian into pieces according to which Plucker coordinate is 0 and which Plucker coordinate is strictly positive. In particular, I'm going to define these pieces as sub m, where m is a collection of sets, k-element subsets of the set of 1 through n. And this is going to record exactly which Plucker coordinates are strictly positive if the set, the label I is in the set M. Otherwise, all the other Plucker coordinates are 0. So in this example, this matrix, you can see all the Plucker coordinates are non-negative, so it represents an element of the positive Grassmannian. And this matrix C represents also an element in this set S sub M, where M is all the collection, two-element subset of a set 1 through 4, except 1, 2, because the Plucker 1, 2 is 0, where all the others are positive. Okay, so this is just a definition. The non-trivial thing is that these pieces have been classified by Poznikov, and also they built on previous work by Lustig and Ries, and they show that basically this their certification was equivalent. And if the species are non-empty, they are homomorphic to open balls. So in particular, we have a decomposition of the positive Grassmannian into cells that are called positroid cells. This M, of course, can be seen as the basis of a matroid, and in this case is a positroid because it comes from a positive matrix. And there is a beautiful combinatorics that is associated to these positroid cells that are in bijection with decorative permutation, Plebby graphs, and many other objects. Okay, now let me move to the amplituhedron. So let me start with this cartoon. So we want to think, we can think about a polytope in m-dimensional space as a linear projection from a bigger simplex upstairs. So this is a simplex of n-1 dimensional with n vertices that projected down to a polytope with n vertices and m dimension, and z tilde is a linear map. Okay, so the question is now, instead of considering a linear projection from a simplex, we would like to consider a linear projection from the positive Grassmannian. And the reason for that is that when you fix k equals 1, the positive Grassmannian is combinatorially like a simplex. So you can see the positive Grassmannian as a Grassmannian generalization of a simplex in this sense. And we want to understand what's down here. So this was the mathematical motivation, if you want to define the amplituhedron. So we fix three positive integers n, k, and m, such that k plus m is less or equal than n. And we fix a matrix Z, which is n times k plus m. So it's a long and skinny matrix, such that all the maximal minors are positive. So once we fix this matrix, we use it to define a map, z tilde, from the positive Grassmannian k comma n to another Grassmannian, which is smaller dimensional, k comma k plus m. And this map is simply matrix multiplication. So if you have an element C from the domain, representing an element of the domain, we just multiply by, multiply by Z. Okay, so we want to consider the image of the whole positive Grassmannian under the Z tilde map inside the Grassmannian k comma k plus m, and this is what it's called the amplituhedron. I will denote this as A sub nkm. Okay, so here is just a cartoon. The amplituhedron is higher dimensional. This was illustrated by an artist. So we can think about the amplituhedron as a generalization of polytopes inside the Grassmannian. And there is also a term called Grasstopes, which is a portmanteau for Grassmann polytopes. Okay, let's look at specific families that we obtain when we specialize this parameter n and k and m. So when k equals 1 and m equals 2, which is, we get the easiest object, which is a convex polygon with n vertices in RP2. And so the vertices of the polygon are just the rows of the matrix Z. And this map is just taking the convex hull, basically. And here, I would get a cone in R3, but then I can choose an affine chart, so I get a polygon of this type. And in general, for k equals 1 and general m, this amplituhedron is just a polytope, a specific polytope called cyclic polytopes with n vertices in RPM. Okay, when k is maximum, so from k goes from 1 to n minus m, when k is equals to n minus m, this matrix Z is a square matrix. And so in the square matrix that is invertible, and so this basically gives an isomorphism between the two spaces, and then this means that the amplituhedron is just a positive Grassmannian. So this object somehow generalizes the positive Grassmannian and cyclic polytopes, if k is in between. There has been studies of other, for other values of parameters. For m equals 1, we have the last case for which this object is actually linear, or polytopial. Yeah, it's kind of linear, because it was proved that by Karp and Williams in 2016 that this is a bounded region in a cyclic hyperplane arrangement. For m equals 2, the object is nonlinear. However, with my collaborators, we show that the combinatorics is related to the combinatorics of the hypersimplex and the tropical positive Grassmannian. So if you're interested in these two objects, you have further reasons to maybe learn about the amplituhedron. But for today, we mostly focus on m equals 4. I cannot write a picture, draw a picture here. This is a picture of scattering amplitudes, because this was originally defined to encode scattering amplitudes in a certain quantum field theory. And the idea here was that to compute the volume, in order to compute these amplitudes, we need to compute the volume of this space. And in order to do that, we want to tile it, to subdivide it, and then sum over the volumes of each tile. And in particular, there was a recurrence from physics that they computed these amplitudes by Brito, Cacciazzo, Feng, and Witten, which is BCFW, that would correspond conjecturally to a tiling of his amplituhedron. Okay, so this is a physics motivation to consider tilings, but let me define properly what they are and also motivate it further. As we can think about a triangulation of a polytope as a decomposition of a polytope into images of faces of the upstairs simplex, we can think about tile the amplituhedron, decompose the amplituhedron in terms of images under the Z tilde map of the upstairs positroid cell. So we have a nice decomposition upstairs into positroid cells, and we like to map it down and consider the images and trying to understand how can we tile the amplituhedron using these images of positroid cells. Okay, let me define what some of these words I mentioned are. If S is a positroid cell in the positive Grassmannian, I want to consider its Z tilde image, and I want to take the closure. So I denote this as a Z sub S. So Z sub S is a tile for the amplituhedron if two very simple conditions are met. If the Z tilde map is injective on the positroid cell, and if the image has full dimension. Okay? So in the case when the amplituhedron, very easy case when amplituhedron is a polygon, tiles are just triangles with vertices on the vertices of the polygon. Then if we have a collection of tiles, then we get a tiling if two very simple conditions are met. The first is the union equals the whole space, the whole amplituhedron. And the second is that the interiors of the tiles in a tiling have to be pairwise disjoint. So it's exactly what you would expect if you want to have a tiling. So in the case of when the amplituhedron is a polygon, we just get tilings are just triangulation of a polygon. Okay, so let me give a bird's eye view on tiles and tilings for general K and M. Okay, so I already mentioned that for K equals 1 and M equals 2, the first line. So for K equals 1, the amplituhedron is a cyclic polytope. So tiles can be shown to be just simplices, m-dimensional simplices, and tilings are just triangulation of a cyclic polytope. Okay, for K equals n minus m, the situation is boring because the amplituhedron is just a positive Grassmannian, and there is only one tile, and there's only one tilings with one tile. So that is a bit boring. But for m equals 2, already this was a very non-trivial thing to understand. And with my collaborator Lauren Williams and Melissa Sherman-Bennett in 2021, we classify all the tiles, and we basically put them in bijection of some combinatorial objects called bicolor subdivisions of an n-gon. And we also show that the tilings of the m equals 2 amplituhedron are in bijection with certain decomposition of the hypersimplex into positroid polytopes. This was, I think, a FPSAC talk 2 years ago. Today, I will also focus on m equals 4, where we show that there is a big class of tiles called BCFW tiles, and that can be used to provide a big class of tilings called BCFW tilings, that are the one exactly mentioned before from physics. Okay. If you want to have a further motivation to explore tilings and the combinatorics of tilings, there is a very nice combinatorics associated to them that comes from this conjecture that we call the magic number conjecture that holds for even m. This was formulated by Stephen Karp, William Tsang, and then also extended by Galashin and Lam, and says that all tilings of the amplituhedron n, k, and m have the same cardinality, which is the number of plane partitions in a box with these sizes. Okay, so it's surprising that an objects like the amplituhedron have tilings with the same cardinality. There are not so many geometric objects that have this property in general, and for sure an n-gon has trivially this property, or triangulations have the same size. But also it will show also the cyclic polytopes in even dimension have this property, and this is conjecture generalized for the amplituhedron for any m. And recently, this was proved in one paper for m equals 2 amplituhedron. In one recent paper, the magic number conjecture for the m equals 2 amplituhedron, with my collaborators, Melissa Sherman-Bennett, Ran Teslas, and Williams. Okay, so this I gave a motivation to study tilings from a physical point of view, from a combinatorial point of view. But going back to m equals 4, in m equals 4, there was this conjecture from physics that the BCFW tilings, this conjecture from physics that was saying that any way of iterating the BCFW recurrence for scattering amplitudes would give rise to a tiling of the m equals 4 amplituhedron. And there was some progress made in 2021, which was proof for a special BCFW tiling that was made of something called standard BCFW tiles. And this was by Evan Zohar, Lark, and Tesler, and this was a talk in FPSAC last year. And recently, with the same authors, plus my collaborators Lauren Williams and Melissa Sherman-Bennett, we proved that any way of iterating this recurrence from physics gives rise to tilings of the amplituhedron. So this is what we call the BCFW tiling theorem. I don't want to go into details about the combinatorics of this tiling, but just as to mention, this is a cartoon to show that if people who know this are in terms of the big graphs, but just to say that the tilings for the amplituhedron with nk, m equals 4 can be written recursively in terms of tilings of the amplituhedron with a smaller n. And there are terms which involves tilings that are obtained by gluing together two amplituhedron with smaller n and k. So this is a kind of recursion. And also here we can see that the cardinality of these BCW tilings is always the same, and it equals the Narayana number. This is interesting combinatorics. Okay. So this is for the BCFW tilings. Okay, so we're interested in studying tilings in general, but in order to prove this, the existence of tilings, or to understand tilings, we of course have to ask the questions of when do tiles overlap, or when we can cover a region with these tiles. And the main insight is that the main protagonist to describe tiles and understand this question is given by the cluster algebra for the Grassmannian M, N. Okay, so I will switch gears to the cluster algebras. I'm not giving a comprehensive review on cluster algebras, this will take too long, but I will mention that cluster algebras are a class of commutative rings with a remarkable combinatorial structure, and they have a distinguished set of generators called cluster variables that are grouped in overlapping sets of the same size called clusters. And these generators have relations among them that are encoded by mutations and also the underlying quivers. So these were introduced by Fomin and Ziewiński, and also there is a nice book that has been being created gradually by Fomin, Lauren, and Ziewiński. And in practice, in order to deal with this cluster algebra, we start with an initial cluster, and then we generate all the other clusters by mutations. Okay. Another notion that is important for us is that we say that a set of cluster variables are compatible if there exists a cluster that contains all of them. So this is quite important for us. We want to focus on the cluster on the Grassmannian, and by Scott was showed that the Grassmannian has a cluster structure, meaning that the coordinate ring on the Grassmannian is a cluster algebra. And for M equals 2 was also shown by Fomin and Ziewiński, and it was proved for general M by Scott. Okay, let me focus in the simplest case for M equals 2. So the cluster algebra for the Grassmannian 2, n has a very simple combinatorics. So the clusters are in bijection with triangulation of n-gon. And then the cluster variables in each cluster are just Plucker coordinates, ij, of the Grassmannian 2, n, that are in bijection with the arcs in the triangulation. So here, for example, this is a triangulation of a pentagon, and here you can see that in the angle brackets are placed on each arcs of the triangulation, and you can see the cluster, the collection of clusters. And also, if you want to, from a cluster, go to another cluster via mutations, the algebraic procedure of mutation corresponds combinatorics to flips of a triangulation to another, so flipping in the diagonal. Finally, we also can easily understand when a set of cluster variables is compatible, meaning that we can find them somewhere in a cluster. We just want to check that the cluster variables, the set of cluster variables corresponds to non-crossing arcs in our polygon. So for example, 2, 4, and 1, 4 are compatible because they correspond to our non-crossing arcs, but 2, 4, and 1, 3 are not compatible because they correspond to crossing arcs, and they will never appear together in a cluster. Okay, so, but for the purpose of today, I want to focus on m greater than 2. And because the cluster algebra for Grassmannian m, n is much more complicated for m greater than 2. And only for the Grassmannian 3, n with n less or equal than 8, there is a finite amount of clusters. Otherwise, there is an infinite amount of cluster. And also, in general, cluster variables are not just Pluckers of the Grassmannian, but are homogeneous polynomials in the Pluckers, and they can be of arbitrary high degree in general. These are not classified, meaning there is no nice combinatorial classifications of all cluster variables. Also, if you give me a set of cluster variables and I want to understand whether they are compatible, meaning I want to understand whether there is a cluster that contains them, there is no easy combinatorial rule to tell that. With the only exception when you give me all Pluckers, in this case there is something called weak separations that I can use as a combinatorial tool to tell whether they're compatible. I just give you an example for the Grassmannian 4,7 here. This is the collection of these cluster variables, a cluster. There is also, I draw also the underlying quiver, but it's not relevant for us today. For example, if you use this to start as an initial cluster, then you can start mutating each cluster variable that is, in this case, in the blue box, you can mutate those ones, and you can generate all the clusters. And in this case, for example, if you mutate 2, 3, 6, 7, you get a cluster variable which is not a Plucker anymore, but is a quadratic polynomials in the Pluckers. So 1, 2, 7, 3, etc. Also, you can see, for example, that 3, 5, 6, 7 and 2, 3, 4, 7 are compatible because they appear together in a cluster here. So this one. Here, but for example, 2, 3, 6, 7 and the quadratic are not compatible because they're obtained from each other by mutation. So they will never appear together in a cluster. Okay, so going back to my original question, how do we describe tiles directly in the Grassmannian? So we want to understand how to describe tiles. Okay, we get back. I just rewrote here the definition of the amplituhedron in case it was a long time ago. So it's an image of a Z tilde map of the positive Grassmannian under the Z tilde map, and Z is the matrix that we use to induce this map, and is a matrix that has rows Z1 up to Zn. So in order to describe the amplituhedron, it's convenient to use something called twistor coordinates, which are more suited coordinates to describe images of the Z tilde map. And if you have a point y in the Grassmannian k, m, I just want to consider these determinants that I denote as y, I1 to im, is the determinant that I get by stacking this matrix y with m rows of the matrix Z. So I have y determinant with m rows of the matrix Z. And this is what I call twistor coordinates. And these are good coordinates somehow to describe the tilde images. Just to give you a flavor, for k equals 1, when the amplituhedron is a cyclic polytope, these twistor coordinates correspond to hyperplanes through some vertices of your polytope. So the vanishing of a twistor coordinates corresponds to the hyperplane passing through these vertices where you can read the labels from that are here. So y13 is the hyperplane passing through Z1 and Z3. So these are very useful to describe the amplituhedron, the images under the Z tilde map. And in particular, we want to consider a key point is that we can interpret a function x on the Grassmannian m, n as a function x of y on the amplituhedron by simply replacing a Plucker coordinates on the Grassmannian m, m with the twistor coordinates yi on the Grassmannian k, k plus m. So as an example, if you give me a function of this type, which is you saw in the previous slides, on the Grassmannian 4, 7, I can immediately write a function x of y on the amplituhedron by replacing Plucker coordinates with twistor coordinates. So these twistor coordinates are these determinants here. And the description of tiles in the amplituhedron will be in terms of this type of functions in terms of twistor coordinates. So okay, the main idea is that tiles then can be described in terms of compatible cluster variables on the Grassmannian m, n that take some definite signs. So under the previous correspondence, cluster variables in the Grassmannian m, n can be thought as functions on the amplituhedron, and that's what we're going to use. So the main conjecture from the paper is that if Zs is a tile of the amplituhedron nk, m, for even m, then there is a collection of compatible cluster variables for the Grassmannian m, n and some sign such that the interior of the tile is determined is in the locus in the Grassmannian k, k plus m, where all these cluster variables have a prescribed sign. So -1 to sigma I is the sign for these cluster variables. Okay, so a very known case is when the amplituhedron is just a positive Grassmannian, as we saw before. The amplituhedron is also, there is only one tile, and the tile is the whole positive Grassmannian. This follows from Scott positivity test for the positive Grassmannian, meaning that the positive Grassmannian can be characterized literally as the locus where the cluster variable of a given cluster are positive. So if you fix a cluster in the Grassmannian, then you just need to demand that all the cluster variables in that cluster are positive, and that guarantees that you are inside the positive Grassmannian. Meaning that if you had to check all the Plucker coordinates to be positive, you would have to check n choose k Pluckers, whereas with this positivity test, you just need to check k times n minus k plus 1, which is the size of a cluster in the Grassmannian, and that allows you to be sure that you are in the positive Grassmannian. Okay, so this can be thought as kind of a positivity test for the tiles in terms of cluster algebras. Okay, so this cluster description conjecture was proved for the m equals 2 amplituhedron in our paper in 2021. So in the last few minutes, I would like to mention the m equals 4 case, which is the cluster description for BCFW tiles. And we basically prove that the tiles that appear in the BCFW tilings, I mentioned in the previous part of the talks, satisfy this cluster description. In particular, there is a collection of compatible cluster variables that I denote as x sub s, where s is the positroid cells that gives you the BCFW tile, that are cluster variables in GR4, n, and there is a collection of signs such that the interior of the BCFW tile is determined by the locus where these collection of cluster variables have a definite sign. The key ingredients of the proof, briefly. So the BCFW tiles, I haven't defined here. It takes a bit of time, but they can be built recursively using three simple operations in the Grassmannian that are called cyclic shift, reflection, and some embedding or insertions of zero columns. And these are, pretty well known. But the key ingredient is called BCFW product, which allows you to somehow glue two smaller tiles to make a bigger one. And so this is the key of the BCFW recursion. And the main point is we can define a map from the two smaller Grassmannian that are associated to these two smaller tiles into a bigger one associated to the bigger tile. And this map maps cluster variables into cluster variables and clusters into subcluster. So we show basically that it's a cluster quasi-homomorphism. And then, using this psi map, we can build this collection of cluster variables for the big tile recursively by applying this map to the collection of cluster variables for the smaller ones. So this is a cluster quasi-homomorphism that was not known within the cluster algebra of 4, n. So it also gives a new way to find cluster quasi-homomorphism. I also want to mention that as a corollary of our work, we also proved the so-called cluster adjacency conjecture for BCFW tiles, which says that the facets of these tiles lie on hypersurfaces cut out by compatible cluster variables for the Grassmannian 4, n. So this was inspired by the physics they introduced cluster adjacency. And the cluster adjacency says that there is a cluster structure in the poles of scattering amplitudes, and was rephrased, these adjacencies were rephrased in the amplituhedron language by me and one of my collaborators. Finally, we conjecture in general that this is true for all tiles of all the amplituhedron, meaning that the facets of a tile in the amplituhedron n, k, m lie on hypersurfaces cut out by compatible cluster variables for the Grassmannian m, n. Okay, so I'm done. The summary and outlook. So the amplituhedron generalizes cyclic polytopes and the positive Grassmannian. And its tiles and tilings have a very rich combinatorics. For example, remember the magic number conjecture. The volume of the amplituhedron gives scattering amplitudes of n equals 4 superior mils as a physics motivation. So we want to compute tilings of this space, and then we would like to maybe sum over the volumes of the tiles. We prove that the BCFW recursions from physics gives a class of tilings for the m equals 4 amplituhedron. And then, of course, the relation with cluster algebra, we prove that the cluster algebra for the Grassmannian 4, n can be used to describe these BCFW tiles, the tiles that enters this BCFW tiling. And finally, in general, we conjecture, and we also show from different cases, and also there is work in progress, that cluster algebra for m, n can be used in general to understand the amplituhedron n, k, m, but also vice versa, that thinking about tiles in the amplituhedron gives us ways to produce cluster quasi-homomorphism to understand better the combinatories of cluster algebra m, n that is, as I mentioned before, deeply unexplored. Okay, this is the main references. If I have like 30 seconds, I would like to read this, and then I'm done. So pure mathematics and physics are becoming ever more closely connected, though their methods remain different. One may describe the situation by saying that mathematicians play a game in which they themselves invent the rules, while the physicists play a game in which the rules are provided by nature. However, as time goes on, it becomes increasingly evident that the rules which mathematicians find interesting are the same as those which nature has chosen. This was said by Paul Dirac in the 39, but I found it quite inspiring for today. Thank you very much. Any questions?
Now we only have time for about 1 or 2 questions.
So I was wondering if the tiles that you have can be used to decompose the Grassmannian into pieces that are somewhat polytopal?
Yeah, in principle, you can define, you can use the same algebraic description for tiles to think about region inside the real Grassmannian. However, I don't know the geometry of those regions, but it is true, you can try to think about these directly in the Grassmannian m, n. This is a open question to understand what's the geometry or the topology of the space.
And one more question.
Hello, thank you for your talk. So just naive question is that, so is there any example where the tile of A, N, K, M is not BCFW tile?
Oh, yes. We show we are sure that, okay, in our paper, we show an example that is going beyond the BCFW tiles. So there are tiles that are not BCFW. And in general, classifying all tiles for m equals 4, and in general for every m, is an open problem. And we also show that there is something beyond BCFW tilings for m equals 4. But the BCFW is the first out of the tower of things. So that's also, at the cluster algebra levels, shows you that there is much more structure that you can explore if you somehow mimic what we've done for BCFW, but for all the remaining ones that we don't know yet about.
Thank you.
Thank you for the question.
So let's save all the other questions for the coffee break, and let's thank Matteo again.